In this lecture, we discuss some corollaries of fundamental theorem of R-Homomorphism. એટલે કે એવા થિયરમ આપણે જોશું કે જેમાં ફંડામેન્ટલ થિયરમ ઓફ આર હોમોમોર્ફિઝમનો યુઝ થતો હોય અને એક્ઝામ્પલ ઓકે સો first theorem is let R be a ring with unity. R is the ring with unity and R module M is cyclic if and only if M is isomorphic to R quotient I for some left ideal I of R. So what is our aim? We want to prove this theorem. First of all, we assume that M is cyclic. So first assume that M is cyclic R module. Now M is cyclic R module, so it is generated by a single element. So M is equal to Rx for some x belongs to M. Okay. Now our aim is to show that M is isomorphic to R quotient I for some left ideal I of R. So we generate I. Okay. So let I is equal to R belongs to R, set of element R belongs to ring R, such that Rx is equal to 0. Okay. So we construct this I. Okay. Now let us consider two elements R1 and R2 belongs to I. This implies that R1x is equal to 0 and R2x is equal to 0. Okay. This implies that R1x minus R2x is equal to 0. So R1 minus R2x is equal to 0. This implies that R1 minus R2 belongs to I. Now every ring is a group. So I is an additive subgroup of ring R. Okay. So this what we are going to show? We are going to show I is left ideal. Okay. So first we have show that I is an additive subgroup of ring R. Now let element R belongs to I and element A belongs to ring R. Now R belongs to I, so Rx is equal to 0. Now multiply Rx by A, so it is also equal to 0. That means ARx is equal to 0. Now the multiplication is associative, so AR into X is equal to 0. This implies that element AR belongs to I. So this shows that I is an left ideal of ring R. So to show I is left ideal of ring R, we show that I is an additive subgroup of ring R, and then after show that any left multiplication of any element from the ring R is also again in the ideal I. Okay, so I is an left ideal of ring R. Now our aim is to show that M is isomorphic to R quotient I. So let us define map F from R to Rx as f of R is equal to Rx. But here it is our Rx is equal to M. So our map is from R to M. Okay. So f of R is equal to Rx where R belongs to R. So first we show that F is an R homomorphism. So let us consider two elements R1 and R2 belongs to R. So f of R1 plus R2 is equal to R1 plus R2x. It is equal to R1x plus R2x is equal to f of R1 plus f of R2. And our second condition is let us consider element A belongs to R, then f of AR1 is equal to AR1x. Now multiplication is again associated. So AR1x, now R1x is equal to f of R1, so which gives f of R1. So f of R1 plus R2 is equal to f of R1 plus f of R2, and f of AR1 gives the f of R1. Okay. This shows that f is an R homomorphism. Okay. Now we saw that f is onto. So let us consider any element W belongs to Rx. Now W is from Rx, so W can be written as R into X for some R belongs to ring R. Okay. Hence for any W belongs to Rx, there exists element R from the ring R such that f of R is equal to Rx is equal to W. Simple way to prove ontoness. Okay. Thus f is an onto R homomorphism. So for what we have seen, F is R homomorphism plus F is 1. Now we saw that F is 1 1. So let us consider two element R1 and R2 belongs to R, and their images are also same, that is f of R1 is equal to f of R2. This implies that R1x is equal to R2x. Now x is non-zero arbitrary element from the module M. Okay, so R1 is equal to R2. X cancel out, we get R1 is equal to R2. That means when images are same, we get the element is also same. So f is 1 1. So f is R isomorphism from R onto Rx. Okay. Now kernel of f is equal to set of all element R from the ring R such that f of R is 0 in Rx. Now set of all R belongs to R, f of R is equal to 0 in Rx is equal to M. Now what is the map defined as f of R is equal to Rx is equal to 0, but this set R belongs to R, Rx is equal to 0 is our I. Okay, so kernel of f is I. We have construct I as this set. Okay, so kernel of f is equal to I, and f is an R homomorphism which is 1 1 and n2 from R to Rx is equal to M. Okay, f is R isomorphism from R onto Rx, but Rx is equal to M. Okay, so by fundamental theorem of R homomorphism, R quotient kernel of f is isomorphic to Rx. Okay, now kernel of f is equal to I, so R quotient I is isomorphic to Rx is equal to M. This implies now this isomorphism is an equivalence relation, so M is also isomorphic to R quotient I. Okay, this gives the proof of our if part. Okay, now the converse part is conversely assume that M is isomorphic to R quotient I for some left ideal I of R. Okay, now our aim is to show that M is cyclic. Okay, we want to show that M is cyclic. Now M is isomorphic to R quotient I for some left ideal I of ring R. Then it is known that left R module R quotient I is generated by the element 1 plus I belongs to R quotient I. ઓકે, એટલે કે જે આપણને R મોડ્યુલ R ક્વોશન્ટ I મળેલો છે એનો જનરેટર કયો છે તો કે 1 પ્લસ I. કેમાંથી તો કે આમાંથી R ક્વોશન્ટ I માંથી. એટલે કે R ક્વોશન્ટ I છે એ સિંગલ એલિમેન્ટ 1 પ્લસ I થી જનરેટ થાય છે. So R quotient I is generated by element 1 plus I. So this can be written as left ideal આપણે consider કરેલો છે. Okay, so this can be written as 1 plus I into R. So this can be also written as R into 1 plus I. Now 1 plus I can be taken as X. So we get R quotient I is equal to Rx. That means R quotient I is generated by single element X. Okay, but M is isomorphic to R quotient I, and R quotient I is generated by a single element X. So M must be generated by a single element of M. Okay, આ એક સિંગલ એલિમેન્ટથી જનરેટ થતું હોય અને M છે આને આઇસોમોર્ફિક છે, તો M પણ કોઈ સિંગલ એલિમેન્ટથી જનરેટ થશે. That means M is equal to Rx for some X belongs to M. એટલે કે M પણ સિંગલ એલિમેન્ટથી જનરેટ થયો. That means M is a cyclic R module. Hence the proof. The converse part પણ આ રીતે પ્રૂવ કરી શકે. ઓકે, તો બંને પાર્ટ પ્રૂવ થઈ ગયા. તો આપણે શું કહી શકીએ? If M is cyclic, if and only if M is isomorphic to R quotient I for some left ideal I of the ring R. This gives the proof of our theorem. Okay, now the next example is, let A and B be an R submodule of R module M and N respectively. Then our aim is to show that M cross N quotient A cross B is isomorphic to M quotient A cross N quotient B. Okay. For that, let us define a mapping F from M quotient A to M quotient A cross N quotient B. M cross N to M quotient A cross N quotient B. Okay. We use the fundamental theorem of R-homomorphism to show this example. Okay. So now we show that F is an onto R homomorphism from M cross N to M quotient A cross N quotient B. And then after we show that kernel of F is A cross B. Then by the fundamental theorem of R homomorphism we can write as follow. Okay. So first મેપ ડિફાઇન કર્યો કઈ રીતે તો કે f of mn is equal to m plus a comma n plus b, where mn belongs to m cross n, where m belongs to m and n belongs to n. Okay, now we saw that f is R homomorphism. So let us consider two element m1 n1 and vector m2 n2 belongs to m cross n. Okay, now f of m1 n1 plus m2 n2 is equal to f of m1 plus m2 comma n1 plus n2. Okay, two tuples here. Now from the definition of mapping m1 plus m2a, second element is n1 plus n2 plus b. This can be written as m1 plus a, m2 plus a, and this element second coordinate n1 plus b plus n2 plus b. Now split this vector into another two vector, m1 plus a, n1 plus b plus m2 plus a, n2 plus b. Okay, this is again f of m1 n1 and this is again plus f of m2 n2. So we get f of m1 n1 plus n2 n2 is equal to f of m1 n1 plus f of m2 n2. Now let element R belongs to ring R and m1 mn belongs to m cross n. Now f of R m n is equal to f of rm comma rn. This now again apply the map f, we get rm plus a, rn plus b. Okay, now this can be written as rm plus a and this can be written as rn plus b. Take r common, so we get r bracket ma m plus a n plus b. So r of f m n. Okay, so we get f of r m n is equal to r f of m comma n. Okay, this shows that f is an R homomorphism. This shows that f is an R homomorphism. Now to show f is onto, let's consider an element wy belongs to m quotient a n quotient b, so that w is the element of m quotient a and y is the element of n quotient b. So w belongs to m quotient a, that means w is equal to x plus a, and y belongs to n quotient b, so y is equal to z plus b for some x belongs to m and z belongs to n. Okay, hence whenever we consider an element wy belongs to m quotient a n quotient b, there exists element xz belongs to m cross n such that f of xz is equal to x plus a z plus b. Now x plus a is equal to w, z plus b is equal to y. So f of xz is equal to wy. This is the traditional method to show f is onto. This show that m quotient a cross n quotient b ના કોઈ પણ એલિમેન્ટ માટે આપણને m cross n માંથી એક એલિમેન્ટ મળી જાય છે કે જેથી જ્યારે એના ઉપર આપણે મેપ એપ્લાય કરશું તો આપણને આ આન્સર આવશે, wy આન્સર આવશે. So this show that f is an onto map. Okay, now we show that kernel of f is equal to a cross b. Now kernel of f is set of all two tuple Mn belongs to M cross N such that f of Mn is 0 in M quotient A cross N quotient B. This gives f of Mn is equal to, હવે M quotient A cross N quotient B ની અંદરના 0 element એટલે A, B. Okay. So now apply the map F. So we get M plus A, N plus B is equal to A, B. Compare both coordinate, each coordinate. We get M plus A is equal to A, N plus B is equal to B. This shows that M belongs to A. કારણ કે જો A ની અંદરમાંથી કોઈ એલિમેન્ટ લઈએ અને એનો આપણે ઇક્વિવેલન્સ ક્લાસ ફાઇન્ડ કરીએ તો પાછો સેમ એ જ આન્સર આવશે. સો M belongs to A અને આના ઉપરથી મળશે N belongs to B. તો આપણે કર્નેલ ઓફ F કેવો મેળવ્યો તો કે સેટ ઓફ ઓલ ટુ ટપલ M, N belongs to M cross N where M belongs to A and N belongs to B. That means kernel of F is equal to A cross B. So what we have shown that F is an onto R homomorphism from M cross N onto M quotient A cross N quotient B with kernel of F is equal to A cross B. Okay. So by the fundamental theorem of R homomorphism, M cross N quotient kernel of F, but kernel of F is our A cross B, is isomorphic to M quotient A cross N quotient B. This gives the proof of our theorem. Okay, this is enough for this lecture. In next lecture we will discuss about the new concept. Okay, thank you.